Hey guys, welcome to your first video of Chapter 7. In Chapter 7, the beginning portion of Chapter 7, we're going to be talking about these ideas of exponential growth and exponential decay. And then we're going to finish up Chapter 7 talking about a very unique concept called logarithms. So a lot coming in this chapter, but the first part of it really is just taking a look at situations where things continue to grow or things continue to shrink. And one of those situations obviously is exponential growth. All right. So first of all, an exponential function is a function of the form y equals ab to the x, where a is not equal to 0, because if a was equal to 0, this whole thing would be 0, right? And again, we call this number here the base. Obviously, we've named that aptly as the letter b for the base. It says that b has to be a positive number other than 1. If the base is equal to 1, you don't get any growth or decay, and again, we'll get more into that in the next lesson. But exponential growth functions primarily is what we're doing in section 7.1. The function grows as the value of b is greater than 1. All right. Now, again, the function in the form y equals ab to the x, where a is greater than 0, again, is going to give you generally a graph that sort of looks like this. All right. So exponential growth is going to continue as x goes to infinity. The function is going to go to positive infinity. So that's kind of our idea of exponential growth. But in any case, the function is going to be growing or going away from the x-axis. All right. The growth factor is my base. All right. My b is my growth factor. That determines how quickly my function is going to grow. And then an asymptote is a line that the graph approaches more and more closely. Basically, it's a line that the graph gets very close to but never really touches. In this case, the x-axis would be an asymptote of this exponential function that I've drawn, because the graph gets really close to the value of y equals 0, but it doesn't actually touch it. All right. So let's take a look at some other definitions as we start taking a look at exponential growth. First of all, the parent function for the exponential growth, parent function for exponential growth is simply y equals b to the x, where b is greater than 1. And again, the key here is to get growth, this has to be more than 1. All right. The next lesson, that number has to be less than 1. But again, that's going to give us decay. We'll get into that more in your following lesson. Again, that's the parent function for the family of exponential functions with the base of b. The general shape of the graph of y equals b to x is shown below. A couple of things that we should be aware of. First of all, the x-axis is an asymptote. So essentially the line y equals 0 is an asymptote. And what that says is that my exponential function is going to get very, very close to 0, but will never actually reach it. We can zoom in on this as many times as we want to with our graphing calculator, for example, and we'll see that that line will always be above the x-axis. All right. It says the graph rises from left to right, passing to the point 0, 1, and 1b. Reason for that is this. If we take the function y equals b to the x power, and I set x equal to 0, to find the y-intercept, we set x equal to 0. So this becomes y equals b to the 0 power, and as you know, anything to the 0 power is 1. So the ordered pair 0, 1 is always going to be on my graph. Now that's going to change slightly as we add a value, what we call our a, our initial value, here shortly. All right. The next piece of that is it also says it goes to the point 1b, and for obvious reasons, if y equals b to the first power, well then it's just when y equals 1, when x equals 1, y is equal to b. And so there's my point 1b and 0, 1, those are both on my graph. It says the domain of b of x is all real numbers, and the range is y has to be greater than 0. Now notice it's not greater than or equal to, because as I just said, there's an asymptote right here, so the graph never actually reaches that, just gets very, very close to it. All right, top of the next page then, we're going to take a look at graphing an exponential function. And so when I go to graph this, now all of a sudden we've thrown this initial value here at you. My a value is what I refer to as initial value. All right, the reason for that is this. In any function y equals ab to the x, if I set x equal to 0, again, that would be my initial value where my graph starts. If x is equal to 0, this whole thing becomes b to the 0, which is 1. And so the value of y is equal to whatever that leading coefficient, a, is. So in this case, the point 0, 1/4 is on my graph. And also, when I put 1 into this function, this becomes 1/4 times 6 to the first power. Well, 6 to the first is 6. and then 6 divided by 4 ends up being 3 over 2, or 1.5. Then, so what we're going to do is we're going to plot those points. So 0, 1/4 is like right in there somewhere, all right? And the point 1, 3 halves is, again, 1.5, it's right in there. And we want to kind of approximate a curve that sort of goes there. Now again, we're assuming that this line never actually touches the x-axis. It's kind of hard to draw that, but you get the idea. All right. Again, there's an asymptote at y equals 0. All right. And so again, my graph should stay just above the x-axis, and it moves up and to the right. All right, so let's take a look at another one. Now, just like before, we've talked about this extensively, at least in Algebra 2a, back when we talked about moving in translations of functions. As we said before, if whatever we're doing, this is our h and k, and so when we talked about absolute value, it was y equals a times x minus h plus k. This was my horizontal shift in the opposite direction, so if it was negative, it moved right. If it was positive, it moved left. This was my vertical translation. Then we talked about vertex form of a parabola. And once again, this was my horizontal shift in the opposite direction of the sign. This was my vertical translation up and down. All right? And so as you notice here, we're going to graph y equals 2 times 3 to the x power minus 2, and then all minus 2. Now again, this seems very, very confusing. It seems like there's an awful lot here. But let's think about the parent of that. Let's think about y equals 2 times 3 to the x power. And let's make a real quick chart here, because when x is equal to 0, let's put x over here and y over here. When x equals 0, y is equal to 2, because again, when I plug a 0 into this function, this becomes a 1, and 2 times 1 is 2. When x equals 1, this becomes 3 to the first power, which is 3, and then 3 times 2 is 6. So the point 0, 2 and 1, 6 are going to be on my graph. So let's make a quick sketch of that, and I'll do that one in blue here. 1, 1, 2, 3, 4, 5, 6, which is right about there. And so I'm going to get something that looks roughly like that. All right, I'm going to change my pen color here, and let's continue now with our translation. Now, since this says minus 2, that's going to move my graph right 2 places. And since this says minus 2, this is going to move it down 2 places. So we're going to take each of these points, we're going to translate them right 2 and down 2. Take this one, right 2 and down 2. And we're going to make that exact same shape. And now we have our translation. All right? Now, since we moved this graph down 2 units, its asymptote is now going to be the line y equals negative 2, because again, we shifted the asymptote from 0 down to negative 2. So basically shifted it, the asymptote down 2 units. So now the domain is all real numbers, because you can put negative numbers in and positive numbers in. And so all real numbers should go here. But the range is y is greater than negative 2. Again, not greater than or equal to, because the graph starts at negative 2. It doesn't quite actually get to negative 2, because that's my asymptote. All right, so why don't you guys try the next checkpoint problem. We'll be right back with a solution. So if I want to graph this function, I now have to graph its parent, which is y equals 2 times 4 to the x power. Forget about the rest of that stuff for right now. Make a quick chart for x and y. And when x is equal to 0, y is 2. When x equals 1, y is equal to 8. All right, and again, you can plug those numbers in yourself and check. So I'm going to draw the original parent function here in red. So this is going to be 0, 2. And 1, 1, 2, 3, 4, 5, 6, 7, 8. And so now I'm going to, this one's going to be kind of a steep one. But we're going to go ahead and we're going to try to make a graph of this thing roughly like that. Now again, I know my asymptote here is at y equals 0. So I know my graph can't continue down past that. All right. Now let's switch pen colors on you here, and let's go ahead and try to graph this guy. Okay, so we'll draw this one in blue. Now what we're going to do is to each of these points, and since that says plus 1, we're going to translate each of these points left 1 unit. So left 1 unit, and this says minus 3, so down 3. 1, 2, 3. Move this one left 1 and down 1, 2, 3. Now, since we moved this thing down 3, we moved the whole graph down 3 units, that's going to move the asymptote down to negative 1, 2, and 3. So I'm going to have an asymptote right in here. And so I'm going to use that to help me draw my graph, which is going to be roughly there. All right, the graphs should be exactly the same shape. I know they might not look like it from the picture, but they certainly are. All right, let's talk a little bit about some buffalo. It says in the last 12 years, the initial population of 38 buffalo in a state park grew by 7% per year. So that means we're taking the initial 100% of the population and we're adding 7%, which is the same as 107%. So every year, we take 107% of the previous population. All right? So it says, first write an exponential growth model giving the number of buffalo after T years, about how many buffalo are in the park after 7 years. We'll get to that in just a second, and then we're going to use our graph to estimate when the buffalo were about 53. All right, so the initial amount, again, my initial amount here was 38. And the percent of increase, the growth rate is 0.07. All right? And so the exponential growth model becomes, again, since it's 100% of the old population plus the 7% we're gaining, that becomes 38 buffalo, and then 1.07, because again, 107% of the previous is 1.07, and we're going to raise that to the t power, all right, where t is the number of years past right now, all right? And then obviously simplify, I've already kind of done that for you because I did that kind of up in the right. So this is my function. All right, number of buffalo is going to be 38 times 1.07 to the t power. Now, using this model, you can estimate the number of buffalo after 7 years is going to be approximately 38 times 1.07 to the 7th power. All right, and then that ends up becoming something in relation to, I would do the 1.07 to the 7th power first, and then I'd multiply it by 38. You get roughly 61 buffalo. All right. Now, unfortunately, I'm running out of screen here, so I'm going to slide this up. So I have to wipe this off. And we'll go on up here. And once again, this was roughly 61 buffalo if you hadn't caught that from the previous part. All right. Okay, so now we want to take a look at a graph of this thing. Now, again, the graph is going to go through 0.38. And it's also going to go through, again, remember it was 38 times 1.07 to the first power. Again, if I want the first year, then I have to go to this first power. And this ends up being approximately 40.66 buffalo. All right? And so if I go 1, I go up to 40.66. And then I'm going to get an exponential growth graph that's going to look almost linear, but it kind of has somewhat of a U shape to it. All right? A better way to get an idea of this is taking a look at our graphing calculator. So we go ahead and we type this function into y1 in our graphing calculator. Again, 31 times 1.07 to the x power. And we go ahead and we take a look at the graph. Now I've already adjusted the window for you so that the window matches this window that we had over here. So we're seeing from 0 to 100 up here and counting by 20. So that's 20, 40, 60, 80, 100. And the same thing this way going across. This goes up to 10 years. Now, as we said before, we can make then, it says, draw a smooth curve to connect these points. Well, again, the graphing calculator does a better job of that. So we're going to estimate when is the population around 53 years, or 53 buffalo. Now, that's kind of hard to see here on the graph. And so we're going to translate that over to our graphing calculator. I want to take a look at how you would do something here. What I want to do then is I want to say, look, here's my original function, y equals 38, et cetera, et cetera. That's my exponential graph. And now I want to graph just the line y equals 53, because I want to find out when does this function equal 53. And so if I pass a line through that, you can see that happens after about 1, 2, 3, 4, somewhere between 4 and 5 years. So my initial graph wasn't a very good one. And then what you can do is you can calculate an intersection there. So option number 5, the first curve is my exponential curve. You can see here I'm on that curve. My second curve is there, and now my guess is it's probably right around in there somewhere. And it tells me that the intersections is roughly 4.9 years. So after 5 years, roughly, we'll have our 53 buffalo. Okay, so this is roughly 5 years. All right, so that's a real good way to take a look at that on a graphing calculator. All right, so going back to our notes then, let's take a look at this idea of compound interest. Compound interest is actually a very practical application of exponential growth, because compound interest says you take some initial amount of money, an initial principal P, and we deposit it into an account that pays interest. So you put your money in the bank and it pays interest. The annual percentage rate R is always expressed as a decimal. All right, and it's compounded n times per year. So again, sometimes your interest is compounded monthly, sometimes it's compounded quarterly, meaning 4 times a year, sometimes it's compounded daily, every 365 days out of the year. And so we're going to take this function and it becomes our initial value, which is P, and then 1 plus the interest rate over n, all to the n times t power, where again, n is the number of times I compound my interest per year. So let's take a look at an example here involving compound interest. When we take a look at this, again, you've got to know this formula. Principal times 1 plus the interest rate over the number of times raised to the nt power. That's just something you're going to have to memorize. All right. It says we deposit $2,900, so that's our initial value is $2,900, into an account that pays 3.5% annual interest. So that's 0.035 as a decimal, because again, our interest rate must be expressed as a decimal. So there's our R. We have our P. The number of times, it says find the balance after 1 year if the interest is compounded monthly and annually. All right. With interest compounded monthly, the balance after 1 year becomes 1 plus 0.035 all over 12, because we're compounding 12 times a year, raised to the 12 times 1 power. All right, so we get to this, and now we're going to simplify this 0.035 over 12. That comes out to like 0.0029, and so inside the parentheses we have 1.0029 all raised to the 12 times 1, which is 12. And now we just go ahead and use our calculator. 2,900 times 1.0029 to the 12th comes out to approximately $3,002.55. All right, remember this is dollars and cents here, so make sure your answers have labels. So my balance is roughly $3,002 with 55 cents in change. Okay, so we grew by about $102.55 over that time frame. All right, now if we compound annually, that means the number of times we compound is only 1. So this is 1 plus the interest rate, 0.035. And we're going to put that over 1 raised to the 1 times 1. Well, 1 times 1 is 1. 0.035 over 1 is 0.035. So this is 1.035 all to the first power. 2,900 times 1.035 to the first ends up coming out to roughly $3,001.50. $3,001.50. And so I'm going to ask you, what's better? Well, obviously, the more times they compound your interest, the more frequently they compound your interest, the more money you're going to have. And so, again, because you're getting interest on your interest more frequently. All right, and that's kind of a banking application of that. So why don't you try the next 2 checkpoints, and we'll be right back with a solution. All right, so for example 2, we're going back to our original function. This was number of buffalo equals 38 times 1.07, and we want to know after 11 years, we simply plug in 11. This is just a plug into your calculator kind of thing. You get 79.98 buffalo, which doesn't make any sense. We're going to round that off to roughly 80 buffalo. Okay. The next example says you deposit $5,000 into an account that pays 3.72%, which is 0.0372. So 1 plus 0.0372. And now it says find the balance after 3 years if the interest is compounded quarterly. Well, quarterly says we do it 4 times a year, so my n is equal to 4. So this is 4 here, and then we're raising that to the 4 times 3 because I want 4 compounds per year, and I want 3 years. All right? So this all simplifies to 5,000, and then 1 plus whatever that interest rate simplifies to, sorry, that is 1.0093 all to the 12th power. And then when I plug all that into my calculator, I get roughly 5587.45. So after 3 years of quarterly compounding on $5,000, you've made about $500 in interest. Well, almost $600 in interest. So that concludes lesson 7.1.